Lecture 13 is going to continue our discussion about variable selection, and we're going to talk about an approach called ridge regression, which is related to this concept of variable selection. I want to do a real quick recap of last lecture and variable selection. So the idea with variable selection, this is definitely not a new idea, and this was studied extensively during the 20th century, is that all the procedures we've looked at, so let's say all procedures that we've looked at, they allow for some set of let's call it capital P features. And we do our prediction, either regression or classification, using these P features, right? We predict Y from these P features, be Y a continuous variable, regression, or a categorical variable, classification. And what we may want to do is we may want to select a, quote, best set of features. And there are a couple of reasons why we might want to do that. Maybe it seems obvious. One of them is for prediction accuracy. And this course is primarily focused on kind of predictive accuracy rather than interpretation of a model. And if I select a best set of features, this can increase my prediction accuracy. And we can understand this in terms of the bias variance trade-off, as I'm going to increase my bias and I'm going to presumably decrease my variance. And we're doing this by decreasing P. So variable selection, when we select a subset of features, basically we are in some way decreasing the number of features. So you might be able to, this gets a bit complicated, but you might be able to better your prediction accuracy by increasing your bias a little bit by using fewer features, but getting a corresponding decrease in variance by decreasing your value of P. We'll put a pin in this here, and we'll come back and talk about this in a little bit. The second reason that we might want to select a best subset of features is maybe just interpretation. So I want to know what features are actually driving the behavior. If I just fit a model with all possible features, it might do well, it might predict well. But if I want to know in the future, so I don't have to measure so many features, maybe I can come up with a more parsimonious set of features to do my prediction problem and do this better. So there's just some kind of interpretation. Maybe I care about the actual features of my model. Maybe I'm trying to understand the science behind my model, and understanding the features that play a role will tell me about that. And a related point is probably to point one, but we'll put it as a third point here, is we talked about extensively last time, which is that the model may be ill-conditioned. For example, if the number of covariates I have is much bigger than the number of observations I have, we saw that kind of a simple linear regression model, that's when I say maybe simple is not the word, a least squares linear regression model, if you have more covariates than the number of observations, you get a non-unique solution, or you don't get a unique solution for beta hat. And so you have a very ill-conditioned model where we don't really have a unique solution, or you'll have maybe P is equal to N or close to N, or maybe our covariates are really highly correlated with each other, and we will get a situation where the solution may be technically unique but is really unstable. And is close to being non-unique. Now, we should note here that many of these issues apply to classification and regression. So this is not just a a least squares regression problem, whether we talk about it classically in terms of that, and that was the context in which this was first studied, and so much of the literature is there. But this is just a general phenomena. Other K&N regression, you could do a variable selection there. For LDA, you could do a variable selection. You have a choice of what variables to include in your LDA model. So many of the things that we talk about here will apply to those as well, although the context of the discussion applies particularly, at least at this level, we're going to talk about in terms of least squares regression, where it's originally developed. These can be applied to more complicated models and are. And we'll get to that as the course kind of progresses there. So let's go and let's talk about, let's do a real quick review of, say, least squares regression. So that's just kind of our regression, multiple variables, but it's regression. And what we saw last time when we looked at this is that beta hat comes from solving a set of linear equations known as normal equations. X transpose X times beta is equal to X transpose Y. And so the stability of beta hat, which is the solution to this system of equations, depends on the condition number, kappa, of X transpose X. X transpose X is basically, as an aside, the covariance matrix of my data, if that means something to you. So we have kind of two pictures you can think of here. If we plot the loss, the squared loss of beta against our possible values of beta. So this is kind of our beta axis here, and we plot L of beta on the y-axis, and we can kind of have two different situations. One where we kind of have a really nice defined parabola, and the minimum gives us a beta hat, and our second situation where we technically might have a minimum, but we have a really flat loss, and this is a very curved loss, L. And the condition number in each of these, here the condition number of X transpose X would be small, well conditioned, and here the condition number of X transpose X is going to be large, or even in the worst case, if you get a real flat likelihood, this thing were perfectly flat along some dimension, you would have the condition number would be infinite. So a very simple illustration of this phenomena is if we consider a model where y is some beta naught plus some beta 1 x1 plus beta 2 x2, and maybe there's some other stuff in the model. And we can ask ourselves a question, which is, what happens if x1 is kind of approximately x2? Or highly correlated is another way of saying this. So what happens when x1 is approximately x2? Our model could equivalently be written as y is beta naught plus beta 1 x1 plus, maybe we'll say approximately, beta 2. But instead of x2 here, I could write x1 because that's equivalently approximately x2. And so this would be beta naught plus beta 1 plus beta 2 x1 plus some other terms. And so this is basically a situation where we either have a large condition number, so our loss is really flat, or in the worst case, it's exactly non-unique. If this equality held exactly, we'd have basically non-unique estimates for beta 1 and beta 2. because what we can say here is notice that I'm not really constrained to choose. I don't have constraints to choose beta 1 and beta 2 separately. There's only constraint on beta 1 and beta 2 is that, if let me say this. If let's say beta 1 hat is equal to 5 and beta 2 hat is equal to, so let's say we apply this first model here and we find beta 1 hat is equal to 5 and beta 2 hat is equal to 10. Okay. If it is true that x1 is approximately equal to x2, then equivalently, we're going to get just as good of a fit. Let's say just as good of a fit with beta 1 hat is equal to, I don't know, 7 and beta 2 hat is equal to 8. Why? Because beta 1 hat plus beta 2 hat equals 15 still. And that is all that we care about, is that the optimal place to be, if we look at our second model where we combine, get rid of x2, whoops, I guess this should have been an x2 all along, right? All it really cares is that the sum of beta 1 and beta 2 are 15, and any beta 1 and beta 2 that sum to 15, so generally, any beta 1 hat plus beta 2 hat that is equal to 15 gives the same fit, or approximately the same fit. And so I don't really care exactly what beta 1 and beta 2 are. I have infinite choice. I could let beta 1 hat be negative 1,000 and beta 2 hat be 1,015. Those sum up to 15. And so if my optimal, might get the solution of beta 1 is 5, beta 2 is 10, but and that gives me some fit. Equivalently good fit on my training data would be to have that negative 1,000, 1,015, because it gives the sum of them the same. And the only real constraint here is that we don't have unique solution for beta 1 and beta 2. What we have is a constraint on the sum of beta 1 and beta 2. So what tends to happen, let's say, when this thing is large, we tend to have problems, and we call them stability problems, where the beta hats run off to plus or minus infinity, right? So in our example here, I could set beta 1 hat as 10,000, beta 2 hat as negative 10,015, right? And you get an equivalently good fit. So what happens when you tend to use, to find these estimates is that the estimates these things can run off to bigger and bigger numbers. As long as they have, some reasonable sum between them, then they're going to be fine, and they're going to be kind of their optimal fit. And so when you get these ill conditioning problems, you tend to get these estimates that run off to kind of plus and minus infinity. And so in comes variable selection. And let's say variable selection, would solve this problem by choosing x1 and excluding x2 from our fit. So one way we'd solve this problem, and we'd get a unique beta hat, so you wouldn't have a problem with the estimates running off to kind of positive, negative infinity, is you basically fix the conditioning of x transpose x by removing a variable, so that the condition number or the resulting now changed design matrix is better. And so the simple example of this one is let's not include x2. It's a redundant variable. Why am I including it in my model? Let's include x1 and not include x2. So here, this is kind of an example. We'll come back to this example when we start talking about ridge regression, but this is an example of what variable selection is doing for us here. So the idea, let's say, behind variable selection is let's try a bunch of models with different, let's say, subsets of variables and choose the best model. That is one way of doing variable selection, and in some sense is all we're doing here. We're just going to try a bunch of different models with including this covariate, including that covariate, and evaluate the models and choose the best one. How do we do this? Way one of doing this, which we talked about kind of briefly last time, is we could penalize a training metric, right? We can't just use a straight up a training metric, because using a straight up training metric is just going to tell us to include as many possible variables as possible, because it wants the most flexible model by including as many variables as possible. And so that's not going to work. We could work with what you might call a penalized training metric. You penalize it if it has too many variables, and use this to choose P. So this is very much way one here is very much the classic way of doing this, which was studied extensively in the 20th century. It is, you might feel really old school, but it is very fast. And so actually has quite some good advantages and can work very, very well. If I have 100 variables and I want to try a bunch of different subsets of these, you're going to need some, how many subsets of 100 variables are there? 2 to the 100, right? So you're going to need a really fast way of trying, a bunch of different models. Probably can't try all 2 to the 100 different models. And so this was extensively studied, particularly related to least squares regression in the 20th century. And there's a lot of really fast techniques for trying out different subsets of variables, evaluating them using a penalized training metric, and then using that to choose the best. So examples of this would be, say, forward, stepwise regression. Let's just say regression. And I'll be brave and really summarize this quickly, which is basically add best, quote, best variables one at a time. So we start with a model with just an intercept term. Then we have some metric. We add the variable that makes it the best, that produces the best one variable model. And then we say, okay, let's look at the best 2 variable model. Let's add another one. So this is the so-called greedy approach, where we add one at a time. Adding the variable is going to take us do the best for us. It's going to help us the most. It won't try all models because it's a greedy approach. So if you talk to Dr. Kincaid about discrete optimization, this is a greedy approach. It won't necessarily try everything, but it's going to try some path through the subsets and produce a set of kind of penalized training metrics. You could also do this backwards. And again, quick summary is that you start with all variables, remove variables one at, let's say remove worst, quote, worst variable one at a time. In either case, it doesn't really matter what way you want to go. if we will get some figure that looks like this, and our y-axis is maybe our penalized training metric. So all I mean by that is it's like RSS, but we add on some term that, you know, increases, that will hurt our RSS if we include too many variables. And you'll get some curve like this if let's say this is like AIC, for example, which is just RSS basically plus some term depending on that depends on the number of covariates. And so if we include two new covariates, it will increase that AIC, that penalized RSS. And you might get, you know, a plot that looks like this. So on my x-axis, I have p, the number of covariates, and basically I'll build my model with the best one variable model, then I'll go and I'll build my best two variable model. Maybe it'll be a bit better, and I'll keep doing this over my possible values of p. Eventually, if you worked with just say RSS, this would keep decreasing, right? Because our RSS would always decrease as we have a more flexible model. If we work with some penalized training metric, eventually it'll get to some minimum and it will start increasing again. And what you would say is, okay, let's choose that value of p here and choose this model. So then we'd say choose this. And backwards stepwise regression would do the opposite. It would start over here with all variables and remove one at a time, all the way down until they get to the one variable model. And again, but you do play the same game. You find the minimum, say AIC, and you'd go with that. So this is way one of doing variable selection. Of course, way two, which we've talked about before, is, you know, cross-validation. And this is maybe, let's say, a more modern approach, but it's much slower. So if you want to test, you know, a whole bunch of subsets, it's going to be much slower. If you're doing this for just something like regression, it's going to be much faster to use the highly optimized, incredibly well-studied kind of variable selection techniques that were developed throughout the 20th century. You don't have to specifically use cross-validation. You could do some kind of train, validate, test split, let's say, but you get the idea. Well, we've talked about this before, and you could do that too. You could, you know, it's that is a maybe more general approach. And so if you're working with something other than, say, least squares regression, that's kind of typically more popular to do. Okay. So before we start talking about ridge regression, let me just say one more thing on this, which is note that you know, typically testing all possible subsets of variables is not feasible, not computationally tractable. Again, if I have 100 variables, I would have 2 to the 100 models. If you have enough data, no way, even if you have a small amount of data, there's no way you're testing the 2 to 100 models. And so you typically, if you use something like forward stepwise or backward stepwise, these are greedy approaches. They will just test some sequence of subsets that hopefully make sense. And there's extensive literature kind of exploring that area, but they're not going to test everything. Now, we might not want to test everything. You might think that the goal is definitely to test everything. However, I would say we might not want to test everything. Or I should say test all possible subsets. And why? Remember that ultimately what we care about is our model building procedure. How well does our model building procedure work? Right? So this is kind of the central thing I'm trying to push in this course, and thinking about when you're building a model for these things as you're not just, you know, your model is not f hat. It's not the actual prediction function. It's not, you know, 10 plus 3x1 plus 7x2, right? You've gone through some procedure to build a model, and that model is going to be applied to new data. And you care about, when you apply it to new data, how well that works. And you care about what process you've gone through to build the model so that when you apply it to new data, it works well. And so if your part of your model building procedure is to do a variable selection, maybe part of your model building procedure is to test all possible subsets, right? Let me just say, one, that testing all possible subsets is a very incredibly flexible building procedure, right? It's incredibly, you're testing every possible subset of variables. So your model building procedure is incredibly flexible. You got all of these different models. If we just use a constrained search, or simpler, or greedy search, gives, let's say, using a constrained or a simpler search gives a less flexible model. And that might be good. You might want to, maybe we should call it model building. Man, I can't spell here. Let's try this again. You might not want to have as flexible of a model building procedure because it might put you in the bias variance trade-off in a better position. You might not want to have just as flexible of a possible model building procedure as possible because you might overfit your data. You might want to lower your variance and pay with a little bit of bias, which would be the second one here. A little less flexible. You won't have as unbiased of estimate of a model. You have a lower, you won't have as a low bias model, but you have lower variance, right? So there's actually kind of not only just computation, but statistical reasons why you might want to not just test every possible subset, because the model building procedure is going to be less flexible, and that might kind of put you in a trade-off, a position that you're more comfortable with, or that's going to actually produce, when you use this procedure to build your model, a better model. Okay. So the first one is high flex, which is low bias, high variance. And this one would be lower flex, which would be higher bias, lower variance, right? So that's kind of a trade-off that one can think about. There might actually be statistical reasons, not just computational reasons, why we might want to not test all possible subsets. Okay, let's talk we ridge regression. So if we go back up to our example here, where we had an ill-conditioned problem, we said that one way we could solve this is with variable selection. So assume, let's just talk about a useful foil for us to compare ridge regression against. And if our variables are standardized, so mean 0, variance 1, okay, and I get my beta hats from my least squares regression, order them by size. So let's say beta hat, absolute value of beta hat 1 is going to be the largest, let's say. Is that how we want to do it? Sure, let's say largest. We'd have absolute value beta hat. So we order them by absolute value of their size, right? And we'd have, say, p of these, and this is kind of how I'm going to denote the order of them. So abs beta hat 1 is the largest one, abs beta hat 2 is the second largest, etc. So here is largest, and here is smallest. It's not totally unreasonable to do variable selection by choosing a threshold. Let's call it t. This is our threshold. And do variable selection by including only the covariates with let's say beta hat I greater than or equal to my threshold there. So we're going to choose some threshold based on, how many covariates I want to include. And we're just going to include only the covariates where their beta hats are bigger than that threshold, or maybe bigger in absolute value than that threshold. So this is what's called hard thresholding. And it's kind of a different procedure that you could think about for doing a variable selection. Maybe it's not the best. If you standardize your variables to the beta hats, the reason I said they're standardized is that the beta hats would then be kind of comparable. If you don't standardize them, the beta hats are hard to compare. If you standardize them, it's not the dumbest procedure you've ever thought about. And it's a so-called hard thresholding estimator. So you could say beta hat hard thresholding, HS sub I, is basically beta hat I from my regression if the absolute value of my beta hat is bigger than this threshold and it's 0 otherwise. So this is a so-called hard thresholding operator, which is basically include it or don't include it. Let's now talk about bridge regression. So we're going to just think about this hard thresholding, and we're going to talk about bridge regression, which is, and next time we'll talk about lasso, which is related to this hard thresholding. So that will just put a pin in that. That will provide a nice foil for comparison. Bridge regression basically says, can I do, it's basically an answer to the question of, can I do variable selection in a kind of, let's call it, continuous way. So for variable selection, I include a variable or I don't. It's kind of this binary choice we have for the variable. You include it or you don't. And there might be many procedures in deciding what you include or what you don't. But the question with the bridge regression is, can I do this kind of in some kind of continuous way? So recall here that for, let's say, OLS, which is ordinary least squares, so just our typical least squares regression, our loss function L beta was what? Y minus X beta squared. Oops, the 2 at top. Okay. And that was the loss function. We decided our beta hat by minimizing this loss function over beta. And that's what we call beta hat. And we saw that sometimes this works, but sometimes this could be an ill-conditioned optimization problem. And we can solve it by doing variable selection. But the question is, can I do that in some kind of continuous way? And ridge regression says, yes, let's do some kind of continuous variable selection. We're going to penalize, we're going to kind of slightly alter our ordinary least squares, our typical regression setup, to penalize if beta hat, or beta, is too large. Why would we want to do that? What does that have to do with variable selection? Good thing you ask. Let's go back to our way back example up here. All right, so this is our example, where x1 is approximately equal to x2. And I made this claim that if we have an ill-conditioned problem, it turns out that our beta hats tend to run off to positive and negative infinity because they're kind of ill-posed or ill-defined, and so you can kind of decrease one and compensate by increasing another, or in some complicated way. This is a toy example, but it could be more complicated. But this is what tends to happen: is our beta hats tend to get really large in absolute value, positive or negative. And so what people did is they realized that one way to solve this ill conditioning problem is to penalize my optimization problem here and say, we don't want beta hat getting too large because that probably means it's an ill-posed problem. And so for Ridge, so let's call this beta hat OLS for ordinary least squares. What we do is we define beta hat Ridge to be very similar. We're going to find our beta hat by minimizing over possible values of beta of L of beta, but then we're going to penalize it by some amount related to the size of beta. So here, this is just the size of beta, right? It's the the norm of that beta vector. So if those are large, that thing's gonna be big. The elements of the beta vector are large, so that'd be big. This lambda is our penalty, some penalty parameter. And typically, although I've written just the norm of beta hat, we don't penalize, we don't actually include in that norm the intercept beta naught. So really, I'm being lazy here. You could just assume that I'm not including that. Really, what I mean here is that this is the sum of the beta squares from 1 to p doesn't include beta naught, right? So you're not going to penalize the intercept. There's no reason to, all it's going to do is screw around with the mean of y. So lambda, our penalty parameter, basically determines how much we penalize, big betas. If lambda hat is 0, we have no penalty. And my Ridge estimate is equal to my OLS estimate, right? If I remove this lambda times norm beta squared, that is just going to give me an OLS estimate. As lambda goes to infinity, beta hat is going to go to 0. And if I penalize it bigger, more, eventually it's just going to send beta hat to 0. And so there's some trade-off. How do we choose lambda? Here's the secret. Choose lambda by cross-validation. That's pretty much how everyone does this, is you're going to choose lambda by cross-validation there. So this is kind of interpretation 1. Well, let's call this interpretation 1 of Ridge. And basically, we're penalizing our least squares estimator so that beta hat doesn't get too big, because we think that means that our problem's ill-conditioned, and therefore the solution is running off to positive and negative infinity, and because the problem's ill-conditioned, and if we control that, we can solve this problem and get an estimate. We're going to look at a couple ways of interpreting this thing. So let's call this Ridge interpretation 2. There's a bunch of ways of interpreting this. We're going to talk about a couple of them today. Ridge interpretation 2 says recall calculus 3, and in particular Lagrange multipliers. Lagrange multipliers say that if I want to minimize some function fx over x subject to a constraint such that some function, say g of x, is constrained, some function of my x is constrained to be less than some threshold t. So this is so-called constrained optimization. In Calc 3, we saw that we solved with Lagrange multipliers by forming some function, let's call it L, scripty L, of lambda and x, which was our function we want to minimize, plus lambda times our constraint function minus that threshold. And our original optimization problem, star, is equivalent to, let's say, minimizing the scripty L of lambda and x. We can minimize this, let's say, for some lambda corresponding to t. So there are kind of equivalent ways of when you form this Lagrange function, you could solve the original constrained optimization problem by solving an unconstrained optimization problem involving this Lagrange function, which is our original function plus lambda times our constraint. So that looks really similar to the formulation we have here. We have some function that we originally want to minimize plus lambda times some, well, maybe that can be interpreted as a constraint. And so what we can do is we can interpret, or we can say, ridge is equivalent formulation. An equivalent formulation of ridge is that beta hat ridge is the beta that minimizes L of beta such that the norm of beta squared is less than some threshold t, and this t is going to correspond to lambda. So there's some correspondence between t and lambda, but that original version where we said it's the minimizer of L of beta plus lambda times that thing squared, the equivalent formulation, which is basically just the Lagrange formulation of it, going back and forth between the dual and the non, whatever, is that this is a constrained optimization problem. So the second interpretation, the first interpretation is a penalized optimization problem. The second is a constrained optimization problem. So we can draw this really nicely in the picture. All of these interpretations are really good for understanding what ridge is doing. Our original beta hat, so let's say beta hat OLS, is here. And if we look at beta hat OLS, if we look at maybe these are our maybe these are our level curves for L of beta, right? It's a quadratic. These are kind of some quadratic level curves. And what we do is we'd find the minimum value. So this is like some bowl shape coming out of the plane, and we have our minimum here, and these are the level curves associated with it. That would be our OLS solution. And ridge regression, you can interpret as a constrained version of this OLS, where I'm going to put some constraint here that my beta hat has to live in this circle, right? That's all this is. It's a quadratic, right? So it's, in reality, it's some higher dimensional circle, but, norm of beta squared in 2 dimensions, beta 1 squared plus beta 2 squared, less than or equal to t. That's just defines some disk, right? So we have some disk here that we're saying our beta hat has to live in. And again, from Calc 3, our solution is where this level curve is going to intersect with our constraint. And so this is our solution here. This is our beta hat ridge. This is a solution to a constrained version of OLS. That is the constraint that is in my circle. It's on the border of it, but it's in it. And it's the minimum value. It's as close as I can get to the OLS minimum when satisfying my constraint. So that is the second way of interpreting this ridge regression. And as a kind of constrained optimization problem, which again, we talked about, we want to make sure our beta hat doesn't get too big, because somehow we think that helps avoid ill-conditioned problems. And our third interpretation of ridge, let's call it interpretation 3, will directly address this. Note here that my loss function, which is y minus x beta squared, and my constraint, beta hat squared, are both quadratic. By that I mean they're the sum of squares, right? And, more importantly, they're differentiable. The fact that for OLS, our L of beta is quadratic and differentiable means that we had a, let's say this means a closed form solution. For OLS, we had a closed form solution of beta hat is x by x transpose x inverse x transpose y, right? That was our closed form solution. And the reason there's a closed form solution is because it's quadratic and differentiable. Differential means, well, the fact those two give this complement, we actually get a nice closed form solution, which isn't always true. And ridge, which is also just, optimizing here, if we go back up to the formulation 1, this is a more complicated function to minimize, but both parts are quadratic and they're both differentiable. The sum of the squares of the beta, certainly differentiable as far as the betas go. And so we're also going to get a closed form solution. So this also has a closed form solution. And the original beta hat, so this was beta hat OLS, came from solving our normal equations, x transpose x by beta is x transpose y. And for ridge, if we take a derivative and we set it equal to 0, it's differentiable, we set it equal to 0, what we're going to get instead is x transpose x plus lambda I, lambda is our penalization parameter, times beta is x transpose y. And so if we solve that for beta, we get beta hat ridge is, well, instead of x transpose x inverse, it's x transpose x plus lambda I inverse by x transpose y. So we get a really kind of similar estimator. What we've done is we've replaced x transpose x with x transpose x plus lambda I. And so our whole conversation, which we talked about for a while last time about conditioning, is that for OLS, we had this whole conversation about how conditioning, whether or not the problem was well conditioned or not, depended on the condition number of x transpose x. And for ridge, what we get is that the conditioning depends on the condition number of x transpose x plus lambda I. And so the idea is that x transpose x may not be well conditioned, but if I take x transpose x and I add on some multiple of an identity matrix, the identity matrix is really well conditioned, right? The condition number of an identity matrix is 1, or any multiple of the identity matrix is 1. So we're basically like an average between a really well conditioned matrix identity, which has an obvious simple inverse, and something that probably isn't well conditioned. And if we add on, as lambda gets larger, we're going to have a better conditioned problem. So I say may, the reality is it will be better conditioned. So basically, this was the original way that ridge regression was proposed, which is to say that, well, x transpose x may not be invertible and not be well conditioned. Let's add on some multiple of an identity matrix to make it better conditioned. Bigger lambda means it's closer, that if I have a really large lambda, then this thing is basically just lambda I, well conditioned, but we tend to move away from our original OLS solution, which was in some ways optimal. For a smaller lambda I, if the lambda is 0, we're going to just get our OLS solution, which may not be unique. So we want some middling lambda that kind of retains enough of our original x transpose x, but better conditions it. So we get a unique solution. We don't run into ill conditioning problems. And so in some ways, this helps solve the... So this is how ridge was originally proposed, was adding on this. And this kind of helps solve some of the, at least the third part of why we talked about maybe you want to do variable selection, which is to solve some of these ill conditioning problems. So when I talk about ridge regression, maybe we shouldn't say that, can we do this variable selection in a continuous way? Maybe the better way to say this is, can we deal with ill conditioning in a continuous way? Because at the end of the day, this ridge regression, which we choose some lambda, maybe choose it with cross validation, and we find our beta hat ridge by solving, well, in fact, there's a closed form solution. You just add lambda I to x transpose x, invert it, multiply by, on the left, by x transpose y. This will give us a unique solution. It won't be ill conditioned, but we didn't actually select any variables. So in some ways, it solves the ill conditioning problem. It's not really a variable selection technique, though. 2 points, and then we'll stop. Point 1 is let's just say, let's talk about this actually for a hot minute here. Let us decompose our design matrix X using the singular value decomposition, U, D, V transpose. So this is why I taught this to you, one of the reasons. If we do this, then, so this is our SVD, we can get a really nice interpretation of what ridge is doing, as opposed to variable selection. In this case, X transpose X is what? V d U transpose by U d V. U is orthogonal, so U transpose U is the identity. This gives us U V, should be transpose there, V d squared, V transpose. So if we look at X transpose X inverse, this is what I'll let you prove. This is, we'll say, V d to the negative 2, V transpose. D is diagonal, so you can just pretend element-wise. So d squared is just the element y square. D to the negative 2 is 1 over the element y square. It's a diagonal matrix. It's really simple. And X transpose X inverse X transpose is V d to the negative 2 V transpose times X transpose, we said, was V d U transpose. V transpose V is the identity. This gives us V d to the negative 2 by D, which should just give us D inverse U transpose. Almost there. And so X transpose X inverse, let's say our Y hat, right, is X beta hat, is X transpose X inverse X transpose Y. And so if we look at X transpose, this is what? U d V transpose, V d inverse U transpose Y, and V transpose V goes away, D inverse goes away, and I just get U transpose Y. So you can write this as the sum over my columns. Let's say there are, how many columns? Whatever, will be vague. Some number of columns of U as Uj transpose Y. So what this is the sum of Y projected onto the jth column of U. So this is for OLS. So for OLS, we can write Y hat as the sum of the projections of Y hat onto this U, the columns of this U matrix. The U matrix, of course, is, these are the columns of U, and they are a basis, somehow some important basis of the column space of X, right? Okay, so that's OLS. We can redo this for Ridge. You ready for it? Okay. If we look at Y hat Ridge, which is X beta hat Ridge, which is X by X transpose X plus lambda I inverse. So I'm going to do this a little fast, but you can do it at home. Right? That would be our X beta hat Ridge, which is X times, we already said X transpose X is V d squared V transpose plus lambda I inverse by X transpose Y. X is U d V transpose, V d squared V transpose plus lambda I, all inverse. And this was, we said V d U transpose, that's X transpose, we get a Y. I can bring in my V's, right? V's are orthogonal, so V inverse is V transpose. I can bring it in. Just recall that, right? I'm going to do a move here. All I'm doing is the AB inverse is B inverse A inverse, right? So I can, if I want to bring B inverse into A inverse, I can do this kind of trick. I'll let you justify the trick I'm going to do, which is that this is UD, and I can bring in a V, but I have to bring it on the other side, the V transpose. And I can bring this V transpose, it turns into a V. So I can basically bring those into the inverse that way. And what was already in there was this. And then I still have my du transpose Y on the outside. Nicely though, if I push my V transpose and my V through, what I'm going to get, I'll get a U and a D. I'll get a V transpose V d squared. And then the other side, I'll push my B through. So all I'm going to be left with here is d squared plus lambda I, right? Because my V's are going to push through. We distribute the V from the left and the right through. All will be left in here is d squared plus lambda I. And on the outside, we left with the d U transpose Y. And don't forget my inverse. Okay, so I'll let you think about justifying some of these steps, but what I'm claiming is true. Notice that everything in this middle thing is diagonal. So it's a sum of two diagonal matrix. It's a diagonal matrix. It's the diagonal matrix with D, which has my singular value squared, plus lambda times 1. So that's all that, all this middle is just the diagonal matrix. And so the inverse of it, and inverse of the diagonal matrix, the sigma I squared plus lambda on the diagonal, is just another diagonal matrix with 1 over sigma I squared plus lambda, right? That would be the inverse of that diagonal. Of course, we have these two diagonal D's on the outside. And so what I'm going to be left with is U times some diagonal matrix. I'm going to have a diagonal D with my, right? These D's are just a diagonal with my singular values on them. And so what I'm going to get is ultimately, I'm going to get a sigma I from one side, a sigma I from the other side. And then if I invert this thing, it is the inverse of this thing. Gives me a sigma I squared plus lambda. And then I get a U transpose Y. So that is how I can decompose my estimates, given from ridge regression. And in a similar way here, when I had UU transpose Y, I could write as the sum of the outer product of the columns of Y, of U times Y. You can similarly write this as the sum of kind of a weighted sum of sigma I squared over lambda plus sigma I squared times uj transpose times Y. And so what this is now a weighted sum of projections of Y onto the uj. So for OLS, you could look at the estimates given to us from OLS, the Y hats, as basically I project my data, my Y, down onto this certain basis of the column space of X. And then I sum that up, right? Now the projection might lose some of Y, which is why Y hat won't actually give us exactly Y, because the column space won't necessarily span the whole space. And ridge does the same thing, where you can think of it as projecting the data down on the Y. If I want to get Y hat, I project it down onto the certain basis of the column space, and then I take a weighted sum. And it's weighted in this certain way. It decreases, right? Sigma I squared over lambda plus sigma I squared is always less than or equal to 1. So what you will often see the ridge regression estimator called is a shrinkage estimator, because it shrinks these components. If lambda is 0, we're going to get 1 and we get an OLS estimator. If lambda is large, it's going to shrink directions with associated with the lower sigma I more, right? If I look at sigma I squared over lambda plus sigma I squared, this gets closer to 0 if the sigma I is smaller. If sigma I is larger, it kind of dominates the equation, so the adding that lambda in doesn't do as much. Okay, so just real quick to finish off here, variable selection basically says this. Here's my three-dimensional space, x1, x2, x3. And what variable selection, I have some data here. And variable selection says, I'm going to remove x3 from this. Ridge regression, here is my thing, and here is my data. Ridge regression basically gets a certain basis of my data. This is basically U1, and maybe this is what we call U2. These are what we're going to call the principal components, which we'll talk about in 2 lectures. And so it projects the data onto this, and then it's going to shrink it's not going to just remove one of the coordinate axes. It's going to basically get a new basis for the space according to these U's, which we'll call principal components. We'll talk about that, but you just think of it as some certain important basis for the space. And then it shrinks. It's going to somehow shrink that direction. It's going to shrink all the directions, but it's going to shrink the smaller directions more. And so it's kind of behaving like a variable selection that removes a dimension, but instead it's just changing basis and then shrinking certain dimensions. I think we'll just stop there. We're kind of at time, but that is a real quick tour of ridge regression. And next time we'll continue talking about ridge a little bit, and we're going to talk about something called the lasso, and we're going to bring it back to talking about variable selection and wrap this all up hopefully next time.